So this will be a lecture on an introduction to special relativity. And I'll divide it really into 4 different videos. The first one here is going to be about the physics in around 1900. And the second part will look at Einstein's perspective on the physics of that day. And third part will be about Einstein's postulates of special relativity. And the fourth part specifically on the relativistic effect known as simultaneity, whether 2 events are simultaneous or not. So again, this first part is just on the physics around 1900. So some physicists around 1900 were beginning to think that the whole discipline of physics was almost done. When you looked at the different areas of physics, one of them was heat. And previously, a kind of an old idea of heat was that heat was a fluid that kind of could flow from one object to another. And in the 1700s and 1800s, as people started developing the atomic theory, it was found that really heat was just the motion of molecules, and that you could explain everything about how heat transfers just in terms of elastic collisions of molecules. So a whole discipline of physics was suddenly reduced fundamentally to mechanics, motions of particles. Similarly, when you look at the fields of electricity and magnetism and light, they had been thought to be totally separate areas of study. And as we saw in the 1800s especially, there was a great unification of electricity and magnetism as Faraday and Oersted and later Maxwell began to understand the laws which show how electricity and magnetism relate to each other. And then finally with Maxwell's equations, as he found out about electromagnetic waves and discovered that the speed of an electromagnetic wave would be the speed of light, suddenly the whole fields of electricity, magnetism, and light all became kind of one thing. So there were those in physics who thought that they'd almost finished the last chapter of the physics book and that there was nothing really important to be studied. There were just a few kind of problems that were hanging around in the late 1800s. And we're going to look at one of those problems right now. And that was measurements involving the speed of light. And we've already measured the speed of light. But one thing that was a question mark, they thought if light is a wave, and Young's experiment and Maxwell's equations all supported the idea that light was a wave, then you should have a medium. You should have something that must travel through. And as often happens in physics, when you're studying something new and you don't know what it is, the first thing physicists do is they name it. And so people called the stuff that light would travel through the ether, or sometimes the luminiferous ether. So we had this ether theory of light. And so once you postulate that there is such a thing as an ether, then you have to begin to investigate what is it and what are its properties. When you look at Maxwell's equations, Maxwell said that light had a particular speed. In fact, he gave an equation for looking at that speed. And let's see if I can just write that equation here. I'll try. His idea was that the speed of light should equal 1 over, we had epsilon naught and mu naught, and we take the square root of that. And you could ask about this equation, well, if that's supposed to be the speed of light, what's that the speed relative to? There was nothing in Maxwell's equations which told you that should be the speed compared to anything in particular. So when people began postulating the idea of an ether that light traveled through, it was assumed that, well, that must be the speed of electromagnetic waves compared to the ether. So at that point, you had a kind of a quest for physicists to begin to measure, can we measure the speed of light from different reference frames, and will we get different results? Because depending upon how you're moving compared to the ether, you might then get a different speed of light compared to you. So I'm going to kind of outline an experiment, and I don't think any physicists did this exact experiment. In fact, I'm sure they did not. But I think it gives you a good idea of what they were trying to do. So you can imagine, for example, suppose we have a car. And we'll say that that car is going to turn on its headlights. So we'll give ourselves a road here. And we'll have some observer here to measure the speed of light. We'll put him down the road a little ways. And let's see. So our car is initially just going to be at rest. And so our car is just sitting here, and it's going to turn on its headlights. So suddenly light is going to begin streaming out of these headlights. And we need to have some way for our observer here to measure the speed of light. So we'll give him a device. That will be a light speed measuring device. That's what it's going to be. And so here we'll go ahead and label that device here. This thing is going to be a light speed measurer. And we'll hand that to that person. And here we go. That thing there. And we then say, well, if the car turns on the headlights, how fast will the light coming out of the headlights here, how fast will that light actually be moving past the person when they use their meter? And I think we know the answer. That's what we've studied. If you just have a source of light which is sitting there at rest compared to your observer over here, then we expect that the person's going to end up measuring that the speed of light going by is going to equal just 300 million times the speed, 300 million meters per second. That's a lot of zeros. So person measures speed of light to be 300 million meters per second. And now we can begin to ask, well, that's fine if the car is at rest, but what's going to happen if the car starts to move? So we'll again just draw the same exact situation, but this time our car is going to be moving. So here's our car. And again, we got our road here. And we'll have our person over here, and they'll be holding on to their meter again. So okay, there's a person, a little bit broken, but you get the idea. And our car, we now have our car moving. Give it some swoosh marks to show its rapid velocity as it moves down the road. We'll say that suppose the car here is moving at the speed of maybe 30 meters per second towards the person, while the person with their light speed meter, so again, the person's still, in this drawing too, there's your light speed meter, okay? Our person's going to be measuring the speed of the headlights as it comes out of the car while the car is moving. So again, our car is moving towards the person at 30 meters per second, and now we turn on the headlights, and that light is going towards the person at 300 million meters per second. And so we need to know what speed will the meter then measure. So we got the 30 meters per second up there. We now have our 3, where I'll just say 3 times 10 to the 8th. That's an 8 up there. Okay, so this is a question, a really important question of the time, because now we're measuring the speed of light from 2 different reference frames. Up above, we've got this reference frame where the source of light is at rest, and the light itself is then moving towards the person at 300 million meters per second. And now we've got a case where our source of light, the car, is moving towards the person at 30 meters per second, and we're wondering what speed they should measure. And I imagine there are 2 different answers you could think of. You could think, well, in this situation, maybe the person would measure, well, you should think about this. This goes back to kind of basic physics, stuff we studied at the start of the year. We're adding these 2 vectors. You've got a moving source, and something's moving away from the car at 300 million meters per second. So shouldn't we just take then the speed at which the light's coming out of the car and add it to the speed of the car compared to the person in order to get the speed of the light compared to the person? So that would lead you to guess then that maybe the speed of the light compared to the person should be 300 million. And now we've got this extra 30 meters per second. That's what we learned from the start of the year. So hopefully as you're thinking of this question, you're thinking, yeah, that's what the answer ought to be. Now maybe you've heard somewhere along the way that the speed of light is always supposed to be a constant thing. And you're thinking, wait a minute, nothing can go faster than light. That's just like this absolute value, a speed limit on the universe. So maybe you're thinking somehow, even though the car is moving, maybe we're still just going to get an answer of 300 million meters per second. And perhaps you're thinking that, but you got to ask yourself, why are you thinking about that? That's not the physics that we learned. Everything we've learned is that you should just be able to add these 2 velocities together. This idea that, if you want to find a velocity, you just add the 2 individual velocities together, the speed of the car compared to the road, plus the speed of the light compared to the car, and then you should get the speed of the light compared to the road. That's what I taught you, okay? So hopefully part of you is saying the answer ought to be A, but somehow maybe you've heard that the answer is B. And this is kind of where things were. People were just beginning to do these sorts of experiments. Again, not exactly this one. The difference between 300 million and 300 million and 30 would be just impossible to measure. But experiments like this were beginning to be conducted, and they were hard to do, but the preliminary measurements seemed to be that the answer was, in fact, B, that no matter whether the car was moving or not, you still got that same speed as 300 million meters per second. And that's really strange. Again, you've got to recognize that that contradicts the physics that we had learned or that everyone believed was going on. So this was just one of those little problems around 1900 that most people thought, well, this is something we just need to figure out. We don't quite have all these things understood, but it wasn't earth-shattering. A lot of physics was just about done, but there were a few outstanding problems like this one that needed to be solved. And that's the end of the first part here.